We're going to finish up section 11.3 with the p-test. So the p-test is wonderfully simple. You can actually prove it with the integral test, but this kind of series where I have 1 over n to some power is going to converge as long as p is greater than 1. Not greater than or equal to 1, but greater than 1. If p is less than or equal to 1, then it's going to diverge. So it's just that simple. Now, sometimes that means you're going to have to work a little bit harder than I just said, but not by much. For instance, let's take a look at the middle example. Does that one converge or diverge?
Converge.
Converge. And on a test, I'd probably appreciate you say converge p equals 4 by the p-test. This one you do have to work a little bit harder. Oh, you know what? With that last one,
That's easy.
I got to give that one some love. There's not too many problems that I could say that was easy in this course. Not at all. But this one we have to work a little bit harder. I guess you just have to recognize what the fifth root of n can be rewritten as. What would be a way that I could rewrite this? 4 over what? N to the
1/5.
Oh, 1/5, sorry.
4 to the 1/5 power. So what's that tell me about the series then? Does it converge or diverge?
Does it diverge?
Yeah, it diverges, right? Because p is 1/5 and p is less than or equal to 1. So it diverges. Wow. P-series is a really nice test. If you can apply it, great. Now, it only applies to things that are in this form or can be written in this form. And that's fine. That's all we need. So one last one kind of like that, at least to start with. Does this converge? That's a 3 there in case you're curious.
Yes, it converges.
Thank you. Yeah. Converges. P equals 3, which is greater than 1. So that's all we need. That's greater than 1. Now, with this one, we're going to go a little bit farther. There's a remainder theorem. You can imagine that even with the most powerful computers, it'd be tough to sum things up from 1 to infinity. You're just going to run out of time and patience, and perhaps money along the way. So what we have is the remainder theorem, and let's see here. Yeah, that's this one right here. Let me see if I can't make that a little bit bigger. Yeah, it's not too bad. So if you have a continuous positive decreasing function, just like our conditions for integral test, then the remainder, that is the difference between the actual true sum, which is S, and the first n terms, is sandwiched between these two terms. Let's see, is that the one I wanted? Let's see. Let's see. Handouts. Yeah, sorry. Yeah, here it is again. So the remainder, that is the difference between the true value, which is S, and your approximated value is the sum of the first n terms, is somewhere sandwiched between these two integrals. So we're going to see if we can't use this to come up with an approximation for, first of all, the sum of the first 10 terms, and then we'll see how good our approximation is. So let's find, for this one right here, I'm going to continue that work and find S as approximated by S sub 10, sum of the first 10 terms, n equals 1 to 10 of 1 over n cubed. Now, this is not something I really want you to do by hand. You could. I wouldn't suggest it. You know, you could write out 1 over 1 cubed plus 1 over 2 cubed, all the way up to 1 over 10 cubed. But this is the age of technology, so let's apply some technology to this. What I'm going to do is, first of all, have my calculator generate this sequence, and then I'll have it calculate the sum of that sequence. So let's see what we can do about that. I'll do that over here, so you can follow along my keystrokes. The only thing that I'll mention is that I do have it in sequential mode. The only difference that really makes is that when I press this key, instead of getting X like I'm used to, I'll get an N. No big deal. All right, so eventually and overall, I want to calculate a sum. You can find the sum by hitting the second key and the list key. And let's go over to math. The fifth option down will be the sum. Sum of what? Well, we need a sequence. So where do we do the sequence? Now you can get it off the catalog menu. I did that the other day. Somebody kindly reminded me that you can get it off the list menu as well. So if I hit second and then stat again, this time I'm going to go over to operations. Again, the fifth one down gives me a sequence. In fact, I get this nice menu-driven thing here. Now, if you've got some stuff already here, you can clear that out. So I'll clear that out and just type in my expression 1 divided by n raised to the third power. My variable is n, that's good. Those two things have to match. The expression is a function of n, and then the variable itself. Scroll down here, I want to go from 1. Where do I want to end? Where should I end this? Anyone know?
10.
10, good. So I want to go from 1 to 10. So let me cut back here, 1 to 10. And then if you go all the way down to the bottom and press the Enter key, it'll paste that command in for you. Now, perhaps because I spent a little time majoring in computer science, I need to see that extra parenthesis balanced. So the number of left parentheses and number of right parentheses should equal. Now we're good. Press Enter, and bam, there you go. So nice way to sum up the reciprocal of the first 10 cubes. So we'll call S sub 10 equals 1.19753, etc. Now, what you could do for future reference or future use is hit the store key. We'll store that in X because we're going to need that. We're going to, oops, I'm getting this domain error because I'm in the sequential mode. It doesn't like me storing non-integer value in N. So, oh well. We'll just deal with it. No, I could probably store that in something else. Let's see. Store it in fit alpha A. There you go. So it's stored in A. Great. Now, from what our remainder theorem is telling us, the true value is sandwiched somewhere between a couple intervals. Let's take a look back at that. So the true value for this remainder has to be sandwiched between two intervals. So let's do a little calculation and come up with these integrals. If n is 10, this one integral is going to be 11 to infinity. The other one's going to be 10 to infinity. All right. Piece of paper here. 10. Oh, 10. That'll be chosen for you by the problem. It's a good question. I pulled this one off of WebAssign. So they asked that you use the first 10 terms in this as an approximation. And 10 should probably be pretty good because, I mean, after you get out to 10, I mean, the terms aren't going to be very big anymore, right? I mean, 10 cubed is 1,000, so 1 over 1,000, it's not that big. It's really going to make a big difference in terms of your overall sum. So, but we'll see. Pause for just 1 second here. So we're going to go back for a moment to the remainder inequality we get from the integral test. And recall that R sub n is really the difference between our true value and, you know, some finite approximation, the sum from I equals 1 to n, the first n terms in your summation. That difference is your remainder, R sub n. What I want to do is I want to come up with an inequality that involves S. So I'll start by replacing R sub n with S minus S sub n. So this here, let's replace that there. Everything else is the same. But because I don't know what S is, it'd be nice to have that in the middle all by itself. So what I'll do is I'll add S sub n to all three parts of the inequality. So S sub n, S sub n, S sub n. So let's add that in and see what inequality emerges. So that would give me S sub n plus the integral from n plus 1 to infinity of f of x dx is less than or equal to S is less than or equal to the integral from n plus or n to infinity of f of x dx plus S sub n. And that's what I was looking for. Basically, it says if I want a nice little range of values for this true value, then what I could do is take my finite sum and then add on this integral as a lower estimate, and then add on this integral as an upper estimate. Say, okay, it's between these two. All right, so this integral plus, again, my S sub n. So let me find that S sub n for both of or for this, well, we already found S sub n for this term. Let's find these integrals. So with our current example, f of x was 1 over x cubed, or we'll call it x to the negative third. And I want to calculate these couple examples. Trying to think if there's a clever way I can do that. Also, in our current example, n equals 10. So that means for the lower limit, I'm going to put in an 11. For the upper limit, I'm going to put in the 10 here. Now let me just calculate this integral, find its antiderivative, and then we'll worry about substituting in the proper limits. Is that kosher? Nah, I don't want to do that. I don't want to do anything too slick and then kind of confuse people. So let me find this one first. The integral from 11 to infinity of x negative third dx. That's the limit as b approaches infinity of the integral from 11 to b of x negative third dx. Fortunately, I don't need to do u substitution here, so I can just jump straight to the happy ending. That's going to be limit as b approaches infinity. Let's see, add 1 to the exponent, that'd be -2, divide by that same exponent, would be -1/2 times x to the -2 between 11 and b. for -1/2 times the limit as b approaches infinity. That's 1/x². So I'm going to have 1/b² minus 1/11². And that gives me the b 242, 1/242.
So this is just the left side?
This is, yeah. Well, this plus our answer that we got earlier, that's our left side.
Okay.
If we do it again, the integral from 10 to infinity of x -3 dx. Let me just, again, jump to the happy ending. I get 1/200. So that's going to be what we're going to use on the right-hand side. So if we plug everything in together, S(10) plus, where was it? 1/242 is less than or equal to S is less than or equal to S(10) plus 1/200. That's going to be our interval. Now you may remember that earlier we stored S(10). It was like 1.9, 19753, etc. And that's going to be handy. Let's go back here. And on the one hand, I've got A. So let's see, alpha and then A plus, how can they give me that? Plus, all right, let me try it again. Alpha A, there we go, plus 1 divided by 242. And then A again, so alpha A plus 1 divided by 200. So there's my limit. Whatever the sum of the first or of all the cubes is, it's between those two values. And then you can pick as many digits out of there as you need to. I think they require 5 in this problem or something like that. So 1.20166, and I'll put it in a 4 is less than or equal to S, less than or equal to 1.20253. So I think what they have on WebAssign is spots for you to put in the upper and lower limits like that. And that's where it's coming from. Nice. Whew. All right. How are we looking with that one? I mean, it's a long one. I think the hard part was just kind of keeping track of the big picture. And it was it's made a little bit easier by understanding what this is. That's our inequality that helps us determine a range for the true value. That comes from the integral test. All right, we'll stop things here for a moment because we're done with section 11.3.